In today's video, we're talking about NMR, a chemistry instrument that helps us understand where normally the hydrogens and carbon atoms are inside of a molecule. We're going to talk just about the basic theory. This can be a pretty complicated topic, but we'll keep it simple, and after a few minutes you'll have a basic understanding of how this instrument works. So let's jump into it. NMR stands for nuclear magnetic resonance. And it's nuclear because we're looking at the nucleus of the atoms, not the electrons, the outer negative electrons. So we're looking at the nucleus. There's a magnet involved in resonance just because, well, there's some resonance as well. So here's the basic idea. An atom has in its nucleus some positive protons. And depending on what the atom is, what element we're talking about, you have so many positive protons. And you also have some neutral neutrons. So like carbon, because it's number 6, has 6 positive protons and 6 neutral neutrons for carbon 12. And of course there are electrons for a neutral carbon atom, 6 of them, that are on the outside of a whole bunch of electrons on the outside of the atom. In NMR, because it's nuclear, we don't worry about the electrons. We're going to strip away those electron clouds, just strip them away, and we're going to look at the atoms inside of our molecule. Now, different nuclei sometimes spin, and we call that spin a nuclear spin. And the atom's nucleus will spin if it has one of two things. It needs an odd number of protons or an odd number of neutrons inside of that nucleus. If it has either of those situations, an odd number of protons or an odd number of neutrons, it will spin, and that will give us some interesting properties. So let's look at just a few atoms that are very common in organic chemistry. We're going to look at hydrogen and carbon. And we'll look at carbon that weighs 12, and every once in a while, maybe 1% of the time, a carbon might weigh 13. Let's remind ourselves what that means. Hydrogen, being number 1 in the periodic table and maybe number 1 in our hearts, has 1 positive proton inside of it. 1 electron on the outside. But strip away those electrons and just look at the protons. 1 proton and 0 neutrons. Carbon 12 has 6 protons and 6 neutrons inside of its nucleus. And carbon 13 has, because it's carbon, 6 protons, but it has 1 extra neutron. It has 7 neutrons in it. Now, if we look at those nuclei, hydrogen with 1 proton has an odd number of protons. So yes, it has a nuclear spin. You can think about that little positive proton just spinning like a top on its axis. How about carbon 12? Well, we said it has 6 protons and 6 neutrons. Those are both even numbers, so no, it does not have a nuclear spin. Now, how about carbon 13? It has 6 protons. Nope, it would not spin either, but it has 7 neutrons, which means it has an odd number of neutrons, so it will also spin. Yes. Now, the ones that spin, they have, anytime you have a spinning charge, you end up with a magnetic moment. So that means a hydrogen atom or the nucleus of a carbon 13, those nuclei, because they spin, are little tiny magnets. And we're going to take advantage of that in our chemistry instrument known as the NMR. And we'll be able to take those little tiny magnets and do something to them and be able to see them. So that means we can see hydrogens. We can peek into the hydrogen atoms of our organic molecules. And we can look at any carbon atom that has that 1 extra neutron. So here's how the instrument works. We take an NMR tube and we fill it up with our organic compound. And we take that tube then and we place it inside of the chemistry instrument known as the NMR. So the NMR they come in all different sizes and shapes. Here's a fairly big one, but the tube goes down inside of this cylinder, down inside of it. Now there are 2 things that NMR is going to do for us. One thing is it has a great big magnet inside of it. So that magnet will influence those little tiny magnets of our hydrogen atoms. The NMR also has a radio wave generator. So it sends radio waves. And just like you might dial your radio into 98.6 megahertz on your FM dial, you also can get instruments that are called 60 megahertz or 400 megahertz or 600 megahertz NMRs. And those talk about the radio waves we're using. So remember, we have a magnet and we have radio waves. So a magnet and radio waves. Those are the two key pieces. Inside of our sample of liquid, we'll have some hydrogen atoms that point up, some that point down, some that point sideways. They'll point randomly in all different directions. So one sample with a handful of hydrogen atoms in it, all of those hydrogens randomly point in different directions. Then when we place it inside of our instrument though, we have what's called a big, strong external magnetic field. And we tend to call that H naught, H with a little zero. So this represents the big, strong magnet of the instrument that we put our sample inside of. So instead of all of the hydrogen atoms being randomly oriented, they all start to line up with that magnet. So every hydrogen atom zoop, lines up with that hydrogen, with the big, strong magnet. Now, if we want, we can take one of those little tiny hydrogen magnets and we can grab a hold of it and we can flip it upside down and flip it over. And then it wants to flip back as quickly as it can back to where it started. So we call these the alpha spins of when they align with the magnet, and we call them beta spin when they don't align with the magnet, when they're opposite. But we can take one of those, we can flip it over, and that takes a certain amount of energy, the difference between alpha spin and beta spin, and we can take it and we can flip it upside down, turn it into the beta spin, and then it would relax right back down to the alpha spin. Now the amount of energy it takes to cause that to flip actually ends up being a pretty small amount of energy. And we can use some invisible light, and we shine that invisible light on our sample, and that invisible light is called a radio wave, or an RF signal, radio frequency. And a radio wave then can cause the alpha spins to flip upside down and relax back into it. They flip, 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 flip. Okay, now, our hydrogen atoms. There's my hydrogen atom, and I want you to remember what's happening here. A radio wave comes in, we cause it to flip to the beta spin, and then it relaxes back down to alpha. Now, when the magnet is this big, then that's when the radio wave causes it to flip. And if we cause it to flip and we have a little detector over here, somebody's eyeball, that's not a very good eyeball, let's make it a blue eye. We have somebody's eyeball. When this is flipping back and forth, up and down, then the radio wave is being absorbed by my nucleus and it does not hit my eye, my detector. Okay, now let's separate that from this other situation. Now let's take our magnet, remember this is just a hydrogen. These are all hydrogens inside of my molecule. And it has this size of magnet for that little hydrogen nucleus. But that hydrogen atom isn't alone by itself. It is surrounded by an electron cloud. And the electron cloud, because it's negative, if the positive proton makes a magnet that when it's spinning in that direction, the negative electron, when it makes a magnetic field, it opposes my little magnet. Negatives would make the opposite kind of. So these electrons are going around and around in a circle, in a loop, and they make a tiny little opposing magnetic field. So when that happens, my little magnet for my proton now is smaller than it used to be. And we'll draw my little yellow lines to show that it shrunk a little bit. So that means the radio wave that was coming in, that was trying to flip it, it only flips it if it's this size, and now that it's smaller, it stops flipping. So here's my little eyeball. Now that radio wave passes all the way through and hits my eye, my detector, then my detector says, oh, wait a minute, I see that radio wave. It must not be flipping, because if it flips, I don't see any light, and it knows that it's not flipping. So here's what we do. We take that little magnet, and remember it's inside of a magnetic field, H naught. We take a little bit more magnet and we add it. So we increase the strength of our magnet. We crank it up and we crank it up. And as we start to crank it up, this gets taller and taller until now the magnet when it takes on that extra magnetic field, is now the size of my yellow lines. So now the radio frequency comes in, it starts to cause it to flip to the beta, and then it relaxes back down, and it flip, 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 and my detector says, wait a minute, I do not see any more radio waves coming through. Those do not come through. Something's flipping. So it measures the strength of that magnetic field and makes a peak at that strength and says that hydrogen is flipping at that field. So what does this mean for us? We end up getting a spectrum, an NMR spectrum that looks something like this. And what I want you to notice is you end up with a peak where you end up a spectrum where you get a couple of peaks. We've got a peak right here, and we've got a peak right here. So let's undo that. Let's make this one a red peak, call that the red peak, and we'll call this one the blue peak. All right, so we get two different peaks. So here's what happened in this sample. We take some methanol, and we have big electron clouds around these three hydrogens. And they're all equivalent. They all are in the same chemical environment, and they all have the same amount of electron clouds around each of those atoms. In those, the little hydrogen magnets had a lot of electron cloud. So there's my little hydrogen magnet. We had an electron cloud, which opposes that. It got smaller. So we had to increase our external magnetic field, increase it, increase it, increase it. And at this magnetic field strength, it starts to flip. This is a higher magnetic field on this side. So we increase that magnetic field, and at this amount of strength of magnetic field, the hydrogens flip. Our detector says, wait a minute, I don't see all the radio waves, and it starts to make a peak. For this hydrogen, its electron cloud is a little smaller around it because it's next to an electronegative oxygen, which sucks the electrons away from our hydrogen atom. The chemistry word is it's de-shielded. Now this one, we have a little magnet. The external magnetic field is small because there's not a lot of electrons, so we don't have to increase it quite as much. That means it absorbs here at a lower magnetic field strength. The basic idea is, depending on how much electron density is around each of these atoms, they show up in different spots in the NMR spectrum. And that is the basic idea of how an NMR works. So I hope that made sense. It's a short little video. You can go back and watch it again. But that's the basic theory behind this. I want you to realize that there's a lot more detail to this. We just kind of hit the highlights. But it gives you an idea. I want you to remember that hydrogen atoms have tiny little magnets for the nucleus, the positive proton, and the radio waves are coming in, causing that hydrogen to flip, and they flip because of the different electron clouds around the hydrogens. So they show up in different locations. We'll get into a lot of detail in further videos on how to interpret that spectrum, but I want you to realize that's the basic principle behind it. So if you like this video, do me a favor and hit that like button and subscribe so you can watch more of these videos on organic chemistry.